Alright, so this is the first video of the week for week 5. Can't believe we're already in the 5th week of school. And we're going to be doing something in this video that I've told you often happens in a physics class. So here's what's going to happen. I'm going to show you a piece of mathematics, and you're going to see it. And you're going to be able to follow each step of what I'm doing. So you'll follow along and say, okay, I understand what you're doing, and I understand that it's true. But what you're not going to understand is, why am I even doing this particular thing in the first place? So you're going to follow what I'm doing, and you're going to understand each part of it, but the question that you're going to ask is, why? So why is this being done? That's going to be the question when you see what I'm about to do. And I told you that sometimes in physics, you'll see your teacher or your professor go through a proof, and you'll say, okay, I follow what you're doing. What I don't get is, why would anybody do this? And the answer, which I told you before, is a smart person figured this out. And we are stealing their answer, are stealing their idea. So I'm showing you this like I'm this genius that came up with this, oh, well, we're going to do the calculation of the blah, 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 and then we'll do this. Like I'm this genius person that somehow came up with it. Absolutely not. This was something that was passed on to me by my teacher, and I'm going to pass it on to you so that you understand a little bit more deeply what physics is about. The first person that came up with this had to sit there and wrestle with the idea for years and years and years probably. And we're just benefiting from their great idea. So you will understand how this works, but if you say, how was somebody able to come up with this idea? That's that thing that we call inspiration or genius. Okay? So here's the idea. We did the buggy lab, and we graphed position, and we had this wonderful graph right here of position versus time. And it starts here at the origin and it goes up like this. So we have position versus time. And if you remember, this meant that the buggy was going forward. And if you look at this, you remember that the equation for the buggy is x equals v naught t plus x naught. And let's realize one thing, which is that for this buggy, x naught is 0. So we would put 0 in here. So for this particular buggy, it actually turns out that the equation is given by x equals v naught times t. Wonderful. I also want to remind you that we came up with this equation doing the buggy lab, and we didn't actually realize that the equation was x equals v naught t. If you remember, we had to remember that, oh, hey, wait a minute. This curve has a slope, and that slope is equal to v naught, which is the velocity, because the rise over the run equals the amount of distance that you cover in a certain time, and that, of course, is the slope. So let's say that we arrive at some position x final. We'll just call it x final. We can do that. At some time t. Okay, so we just do that. Okay, let's just say that that happens. So we arrive at some x final at time t, like that. We're there. Now, once again, I'm showing you an idea that was taught to me by somebody smarter than me. So I've done that. Write that down. Now, we're going to leave this graph alone for a second, and we're going to do something new here. Again, why am I doing this? I'm stealing an idea from somebody who is much smarter than me. We're going to change gears a little bit, and I'm going to now plot the velocity of this graph, of this buggy versus time. So if you remember, the slope is v naught, and that's a constant slope. A slope of a line never changes. That's something you should remember from Algebra 1. Okay, so this slope, the rise over the run, is always the same for this line forever and ever and ever. So what that means is if we plot the velocity versus time here, this value here would be v naught, and we just get this nice flat line like this. Now, let's also go out to time t right here. Okay. Now, what I want to do is, in this graph here, I'm going to show you a trick. Okay. So if I were to look at this graph right here, if I were to go out to some time final, okay, I'll just call it t final, I am at position x final. Okay. Again, so I'm just picking a point. I'm saying pick a point. When do you reach that point? So when I reach t final, I'm at this time x final. I'm just there. And if I were to write that down, I'd say, okay, I reach some x final at t final, and this just happens to be true. Once again, you say, well, okay, I get it. I have this equation, so you're just writing this point down? Like, why are you doing that? Don't worry about why. Again, a smart person showed me a trick. Now I'm showing you the trick. Here is the trick. Draw this dot, call it x final, and it happens at t final right here. Just write that on your paper. Okay. Now, on the velocity graph, let's go out to the same t final on this velocity graph. So we're out, you actually count the number of squares, and I'm saying 6 squares is out to t final. So 6 squares out to t final. Okay, so you've done this, you don't know why you're doing it, like, okay, I'm labeling this thing on my graph, I guess I'm fine with that. Now here's what you're going to do. We're going to draw a dotted line from t final up to the top. And what we're going to do is this. Again, here's the crazy idea that the smart person came up with. For no reason whatsoever except that a smart person showed me this, I am now going to calculate the area of this rectangle. So we have the height and we have the length of this rectangle. Remember the height, well, if we look here, oh, it's v naught. And the length is equal to t final. So if I get the area of this curve, it ends up being length. Sorry, not length times height. Let me reset that. That's actually going to be area's length times width. So the width is t final, and the length is v naught. Let's get those letters right. So the area of this curve ends up being v naught times t final. So if you notice something, if I calculate, this is the answer, this is the thing that the genius person came up with. They realized if I take the area of the velocity curve, the velocity graph, for the buggy lab, I get this number v naught times t final. And this is exactly equal to the displacement that I got here. So it turns out, if I take the area of the velocity graph, I get the displacement of the car. That's this big, amazing thing that they discovered. Okay? And you say, okay, I can do this calculation. I see that these two things, why are we doing this? The answer is, once again, I am showing you something that you never would have cared or bothered to notice before. No one would care about this. I get that. Here's the point, though. Someone smarter than us saw this, and then they were able to do something very, very clever with it. So this one is true and obvious. And you're saying, well, I get it. I just don't know why we're doing it. And the answer is because somebody smarter than us did it, and then they were able to do one more interesting thing with it. So if I were to relate the area under the velocity curve to the displacement, here's what it is. The area equals the displacement. Okay. Now, here's what we're going to do with the ramp lab. So when we look at the ramp lab position, we know that it's going to be a curve because it's speeding up. Okay, and if you remember, we never really calculated why this was. We just sort of accepted this. So right now, we're just buying this. Right? So we just buy this because Mr. Abdullah said it was true. So accept it. because Mr. Abdullah said so. Okay, now, here's the idea. I'm going to steal the idea from this page before, okay, which is the area under the velocity curve is the displacement. So we did that proof. What we're saying is that's true for all graphs, okay? Or rather, here, so for the ramp lab, if you remember, we had a straight line, v versus t, and we had the equation v equals at plus v naught for its graph, okay? Sorry, plus v naught for this graph, the initial velocity. Now, in this problem, what we have is that v naught is 0. V simply equals a times t. So now here's what we're going to do. We're going to go out to some t final right here. 1, 2, 3, 4, 5. Let's just go out here to some t final. And we'll do the same thing here. 1, 2, 3, 4, 5. So out to t final right here. Just like we did in the previous part. So out to t final, out to t final. So now what I'm going to do is I'm going to do the same thing. I'm going to take the area under this whole graph here, just like we did in the problems. Okay? And what I'm going to say is, okay, if I go out here, this is a y-coordinate, so I use this equation to calculate what that is. I'm going to get that v final equals a times t final. So now, I go up to this height here, so base times height. The height here is v final, and the base is t final. To get the area under this curve, the area is 1/2 base times height. Now when we do this calculation, we get area equals 1/2 times base, which is t final, times height, which is v final. And now we're going to plug in the numbers. Area equals 1/2 times t final, and now I substitute a times t final. So I get that the area is 1/2 a times t final squared. So it seems that when we start from rest, what we get for our position is, the position is 1/2 a. Now, I'm going to lose the subscript. Don't be scared. I'm losing this subscript to show you a general rule. I'm going to write this as t squared, like that. So it turns out that if I start from rest, my displacement is given by 1/2 at squared using this idea. So I'm using this idea for the buggy lab, and I'm extending it to this curve here to tell you, aha, the position is given by 1/2 at squared if I start from rest. Now, here's the tricky part. If I start from a speed greater than 0, you can do that thing that I told you to in class, where you actually have two graphs. So this will be v naught, this will be v final, and this will be t. And what you can actually do is if you get the area under this whole thing, okay, what you'll get is that the displacement equals 1/2 at squared plus v naught times t when you do all the algebra. And so what we'll end up getting is the formula that we had before. X equals 1/2 at squared plus v naught t plus x naught. Now I'm going to tell you something right now. You are watching this video and you are taking notes. I want to be very clear on this. I am making you do this, but these algebraic proofs, and they are pure algebraic proofs, are not on your exam. Okay? What you must do, you must know how to calculate with real numbers.